In today's video, we're going to cover graphs and minimum spanning trees. Specifically, I'm going to show you a simple implementation of Prim's algorithm. The program we create will allow us to easily create and manipulate graphs so that we can easily test Prim's algorithm on different combinations. So to start, let's review the concept of a graph in computer science. A graph consists of a set of vertices with edges connecting them. Let's say that the set of vertices in the graph are represented by the variable v, and the set of edges are represented by the variable e. We can then define a graph G as consisting of a set of vertices and edges. Let's consider this graph as an example. We can see we have 6 vertices present, so we can define the set V as being the set of elements from 1 to 6, and then we can define the set E as being all the edges connecting these vertices. So we can see we have an edge connecting 1 and 2, 1 and 4, 1 and 5, and then we have edges connecting 2 and 3, 2 and 5, and 2 and 6, and then we have edges connecting 3 and 6, 4 and 5, and 5 and 6. To represent a graph structure in a programming language, we use the concept of an adjacency matrix. Say that we have n vertices in our graph, then the adjacency matrix can be represented by an n by n matrix where each entry indicates the length of the edge between two vertices. So let's use the iterator I to represent the row of the matrix and j to represent the column. Each ij entry then tells us if there is an edge from the vertex I to the vertex j. Anything greater than 0 indicates an edge, and if it's 0, we don't have an edge. The example above shows a weightless graph where each edge has a length of 1. We can see this in the adjacency matrix where the edge connecting 2 and 3, for example, is inputted as 1 in both entries of the adjacency matrix. Let's see what would happen if we added weights to each of the edges. Now our adjacency matrix is different. For example, if we look at the edge connecting 2 and 3 again, it's now 5 in the adjacency matrix. For our first order of business, we want to be able to create a graph in C++. In my project, I have created a few files to help us accomplish this. I don't want you to waste time writing every line of code, so I have some skeleton code already defined in these files to help move things along. Let's begin by looking at our files for representing the graph. So first we have our header file graph.h, and in this file we create an empty adjacency matrix using the STL's vector class. This adjacency matrix is going to hold weights which are represented by decimal numbers, so we specify type double for this 2D vector. We also have 2 member variables for keeping track of the number of vertices and number of edges present in our graph, and we want to be able to easily manipulate and access information from our graph, so we have some public methods set up to help us accomplish this. First, we have the initialize method, which just initializes the number of vertices in the graph, and the number of vertices is given by the parameter m. Next, we have the add edge method, which inserts an edge of weight w between vertices u and v. Then we have erase edge, which erases the edge between vertices u and v. And we also want to create a method isEdge, which tells us if an edge between vertices u and v with weight w exists. We have another method degree, which is just going to tell us the degree of vertex u. The degree of a vertex is simply the number of edges connected to the vertex. Next we have the method edgeCount, which just returns the total number of edges present in the graph. We also have a clear method to delete all these edges, and a print method to output the contents of the graph. Lastly, we have the MST method, which takes an integer parameter u, which represents the starting vertex of our MST. Now we'll navigate to our graph's source file, and the first thing we're going to do is initialize our variables num vertices and num edges. In the constructor, we'll initialize these to be 0, and then in our initialize method, we'll set num vertices to be equal to the parameter m, and then we'll call the resize method on our adjacency matrix variable. We'll say add matrix.resize, and then we'll pass in the arguments m. And then for the second argument, we'll pass in a vector of type double with m items all initialized to 0. For the addEdge method, all we need to do is assign the correct entry in our adjacency matrix to be the value of w. What we're trying to do is add an edge between nodes u and v. Recall from our discussion on adjacency matrices, each row has n items and each column has n items. So if, for example, we had a 4x4 matrix and we wanted to add an edge between vertices 1 and 2, we would need to change the value in row 1, column 2, and row 2, column 1. This is because each entry in a row describes the edge between that vertex and the other. We're also going to increment the num edges variable by 2 to show that we've added an edge both between vertex u to v and v to u. Erase edge is going to work the same way as add edge, but instead of assigning a weight to an entry in the matrix, we're going to reset it back to 0. We're also going to decrement the num edges variable by 2 to show that we've removed the edges connecting u and v. Then in isEdge, we're going to verify the existence of an edge by checking that both uv and vu entries in the adjacency matrix are equal to the given weight. In the degree method, we want to check the number of edges the given vertex has. To do this, we have to loop through the row given by u in our adjacency matrix. If the entry is non-zero, that implies an edge, and we can keep track of this by incrementing our count variable. At the end of this function, we can simply return this count. That gives us the degree of our vertex. Edge count is fairly straightforward. We're just going to return the number of edges given by the numEdges variable. And for clearing the graph, that just means setting each entry in the adjacency matrix to 0. To do this, we're going to loop through each row given by numVertices, and then in each row we're going to loop through each column, and in each column we're going to assign each ij entry to be 0. For printing the graph, we're going to do something very similar to what we did for clearing. First, we're going to get the size of the adjacency matrix, then we're going to print one row per line. So to do this, all we have to do is loop through each row and then each column and print the ij entry. Then at the end of each row, we're just going to print a new line so that each row is on its own line when it's printed to the console. Lastly, for the MST function, we're going to leave it empty until we get to the implementation of Prim's algorithm. Before diverting away from our graph source file, there are a few more changes I want to make. First, for the addEdge function, I want to check the false case. So what we're going to do is check to see if any of the input parameters are outside our appropriate ranges. So if u is greater than numVertices, v is greater than numVertices, or if u or v is less than 0, or if the weight is less than 0, we're going to return false. Then we're going to change the way we increment our numEdges. So we want to only increment numEdges if it's a brand new edge we're adding into our adjacency matrix. So if the entry in the adjacency matrix is currently 0, we increment by 1, otherwise we leave it as is. And we need to do this for both uv and vu in the adjacency matrix. Then we'll remove the previous code we have for incrementing numEdges and simply return true at the end. We also need to make a similar change for erasEdge. We're going to copy the conditional we had for the false case and paste it at the top of erasEdge as well. And then we're going to change the way we do numEdges decrementation. So we're going to copy what we have for addEdge, but then we're going to subtract by 1 in the case that the adjacency matrix entry is not 0. We're only going to decrement it if it exists currently, so we remove it only in that case. Then at the end of this function, we can return true. Then we can scroll all the way to the bottom of our file, and then for the MST function, we're just going to return a double 0.0, just temporary until we actually solve our MST function. For testing, I have the MST Prim test file, which is equipped with various commands to help you test different parts of the graph. To compile this code, we're going to enter this line into our terminal, and then we'll run our MST Prim driver. We'll start by entering the command i4, which is just going to create a graph with 4 vertices, and then we'll insert an edge between vertices 0 and 1 with weight 1. Then we'll add another edge between 1 and 2 with weight 2. And lastly, another edge between 2 and 3 with weight 3. This creates the simple straight line graph shown here. You can also print this graph now, which will give us the adjacency matrix representing this graph. As we can see, this matrix resembles what we expect, with each row showing a non-zero value where we expect an edge to be. We can also try out the rest of our commands to make sure they're working. So deg0 should output a degree of 1, deg1 should output a degree of 2, deg2 should also output a degree of 2, deg3 should output a degree of 1, and edge count should output an edge count of 6. That completes all our commands except for the erasEdge command. Let's try to keep our graph connected when erasing an edge. So first we'll insert an edge between vertices 3 and 0, and then we'll erase the edge connecting vertices 0 and 1. That results in the following graph. So if we print this graph now, we can see that our new adjacency matrix represents this change. Note that the new adjacency matrix has different values for rows 0 and 3 now compared to the previous. Now that we have a program for creating and manipulating graphs, let's work on solving the MST problem. When we have a connected and undirected graph with weights on each edge, the MST problem deals with finding the subset of edges with minimum total length connecting all the vertices. To give you an example, consider this graph shown here. This graph is rather trivial, and we can find the MST easily just by inspection. Look at each vertex and just select the edge that goes to an unvisited vertex with the smallest weight. We'll start with vertex 1 and begin building the MST. From vertex 1, we have 3 edges connected to 2, 4, and 5. The shortest edge is connected to vertex 2, so we add this to the MST. Now we look at the second vertex. This has 3 new edges connected to 3, 5, and 6. The shortest edge now leads to vertex 5, so we add this edge to the MST. Vertex 5 has new edges connected to vertices 4 and 6. The shortest edge leads to vertex 4, so we add this to the MST. We can see there is another edge connecting vertex 4 to vertex 1, but since this has a higher cost than the edge we selected, we don't include this edge in the MST. Now we go back to vertex 5. There's an edge connected to vertex 6, but we see that the edge connecting 2 to 6 is shorter than this edge. So instead of adding this edge, we add the edge connecting vertices 2 to 6 to the MST. Now we can look at vertex 3, which is the last remaining vertex to be added to the MST. We can see that in this case there are two valid options. We can either add the edge connecting vertices 3 and 6, or the vertices connecting 3 and 2. They have the same cost, so ultimately either option is correct. I'll add the edge connecting vertices 2 and 3 to the MST. So now we have an MST for our graph, but why exactly do we care about this? MSTs serve a crucial role in networks such as telecommunications, water supply networks, and the electrical grid. Some approximation algorithms also require using an MST. For example, the traveling salesman problem can benefit from using an MST. The traveling salesman problem is all about finding the shortest path that visits each point at least once, so it somewhat relates to the MST problem. Now let's talk about Prim's algorithm and why it's needed to solve MSTs. The graph we were looking at previously was fairly simple, but even when building the MST for this graph, there was some ambiguity involved in which edges belong to the MST. Prim's algorithm gives us a systematic way to solve MSTs in a way that can be easily interpreted by a computer. If you have experience working with algorithms, you may have previously encountered Dijkstra's algorithm before. Understanding this algorithm is imperative to understanding Prim's algorithm because the two are closely related. The point of Dijkstra's is to find the shortest paths between vertices on the weighted graph. Basic idea is to do the following. Maintain an estimate distance v of distance from S to v. Ensure that this estimate is never smaller than the true distance. Keep track of a set H of vertices whose dist values may yet be correct. Then select the vertex v in H that has the smallest distance estimate. Remove v from H and recalculate the dist estimate to all vertices u connected to v. The main component of Dijkstra's that affects runtime is the choice of data structure used to store the vertices and their current distance estimates. We call this data structure a priority QE. This structure maintains a set of elements along with a numeric key value for each element. This structure contains the following operations: insert, which adds a new element; decrease key, which decreases the key value for an element; delete min, which returns the element with the smallest key value and removes it from the QE; make QE, which builds the priority QE from a set of elements and associate key values. The way we implement this data structure is also important. We can either use an array or a binary tree, but using a binary tree is much faster than using an array, so we're going to aim to implement the priority QE as a binary tree. For our priority QE, let's look at our currently defined header file. In this header file, we start by defining some member variables, where the first member is for our actual QE, which stores a pair of values for each entry. The pair contains an integer to represent the vertex and a double to represent the key or current cost of that vertex in the QE. We define this as a dynamically allocated array that will be initialized in the constructor. We have another dynamically allocated array labeled IDXMap. This is going to hold integer values, and we need this array to keep track of the location of each vertex. This helps us edit the vertex key in O1 time. Next, we have our cap variable, which we're going to use to keep track of the number of vertices currently in the QE. We also have a total variable, which stores the number of vertices we initially defined. Lastly, we have 6 private methods. These methods are for managing the tree nature of the heap. We have methods to get the parent, left, right, insert a vertex, and heapify the QE. The public functions we have defined are going to manipulate the priority QE. First, we have the constructor, which takes an integer and an array of doubles as parameters. We're going to define a destructor as well to clean up the dynamic arrays. Then we're going to declare the following functions: isEmpty, which is going to check if the QE doesn't have any values; inQE, which checks if a node is in the QE; delete min, which is going to pop off the top of the QE; decrease key, which takes 2 parameters, an integer v and a double new val, and this is going to reassign the key of the vertex to be this new val. Lastly, we have print QE, which just prints the QE. We're not going to use this function, but it's useful if you're debugging and if there's any problem you encounter when following along with these instructions. In the source file for the priority QE, we'll start by building out our constructor. First, we'll assign the member variables cap and total to the parameter v, and then we'll create a dynamically allocated array h of v pair type objects. We'll do the same for our IDX map, creating v number of integers. Next, we'll loop through v times, and for each iteration, we'll insert a new entry into our priority QE. Each entry in the priority QE consists of the vertex and a key value associated with that vertex, so we'll pass an I and ci to this function. Then we'll store the current index value of the vertex in our IDX map. The D structure is responsible for cleanup, so inside this function, we delete our 2 dynamically allocated arrays and then reassign them to the null pointer. The Parent method is for finding the index of the parent in the heap. So to do this, all we need to do is return I minus 1 divided by 2. In the left method, we want to find the index of the left child for the ith vertex in the heap. So for this, we return 2 times I plus 1. Likewise, for the right method, we look for the index of the right child, so we return 2 times I plus 2. Then, in the insert method, we need to store key value pairs into our priority QE. So we do h idx, and then we set this equal to a key value pair of idx and val. Then we call heapify up to resort the heap, passing in idx as our argument. We call heapify up here because we want to maintain a min heap, so we need the smallest value at the top. In our heapify up function, we want to keep swapping the nodes until we have a new root node. What we're going to do is create a while loop with the following conditions. While I is not equal to 0, so until we reach the root node, and while the parent of our current node represented by I has a key value greater than the current node's key, we're going to keep looping. Then in this loop, we're going to start by swapping the current node with the parent. Then we're also going to perform the swap in our IDX map. So we reassign the ith vertex inside the priority QE to be this value I, and then we also reassign the parent in our priority QE to be the parent of this value I. And then we assign I to be our new parent vertex, and then we keep going until the priority QE is sorted with the vertex with the minimum key value at the top. In the heapify down function, we're going to implement merge sort to create a minimum heap for the tree. We're going to create a recursive function to implement this algorithm. We start by creating 3 variables: smallest, which is going to hold the value I, L, which is going to call the left of this vertex I, and R, which then calls the right of this vertex I. Next, we have 3 conditionals. The first is to check if L is less than the cap variable and the key of the left node found in the QE is less than the smallest node found in the QE. If it is, we need to reassign the smallest node to be this left node. The next conditional is for the right node. We check that R is less than the cap variable and the key of the right node found in the QE is less than the smallest node found in the QE. If it is, then we reassign smallest to be equal to this variable R. The last conditional we're going to add checks if the smallest variable was reassigned. So we're going to see if smallest is no longer equals to I, and if this is the case, then we need to do some swapping. So we're going to swap hi and h smallest in the QE like we did in heapify up, and then update our IDX map. Lastly, we call the heapify down function, passing in our smallest variable as the argument to our parameter. For the isEmpty method, we use the cap variable to track how many elements are currently in the priority QE. So if cap is equal to 0, that means we have no elements and our priority QE is empty. So we simply return the result of this comparison. For the inQE method, we don't have a time constraint on how fast we want to find the vertex, so we'll just do a simple linear search. We'll just iterate over all the vertices until we find the vertex that we're looking for, and if we do, we'll return true, otherwise we'll return false. If you want to speed up the execution of this program, you can use a different searching algorithm like binary search. In the delete min method of the priority QE, we want to pop off the top of the QE and return it to the calling function. So we start by making a copy of the top element of our priority QE, and then we reassign the top so we get rid of it. So we set h0 to be the last element in the priority QE instead, and then we also reassign the value in our IDX map. So we'll set the root element in our IDX map to be -1 now to show that it no longer exists in the priority QE. Then we'll reassign the new IDX map value to be 0 to show that the last element in our priority QE is now the top element. Then we decrease our cap variable to show that there's less elements in the priority QE now, and then we call heapify down, passing in 0 or our root node as the argument. So now heapify down will resort our priority QE starting from the top and going all the way to the bottom, moving elements along the way to make sure that the minimum element is again at the top. For the priority QE's decrease key method, it's fairly simple. We have 2 parameters, v and new val, and all we need to do is find the index of this vertex v and then change the key in our priority QE to be this new val. Now since the key is different when you resort the priority QE, so we call heapify up. In heapify up, we pass in as the argument the index of the vertex v. Heapify up will check the parents of this vertex to make sure that those vertices don't have a key value less than this new val. Print QE is very straightforward, so I'm not going to go over the code over here. All we do is iterate over the QE contents and print each item, same for the index map. Back in our graph source file, we're going to start working on the MST function. First, we're going to define a prev array and a cost array. we're going to dynamically allocate these arrays to be the size of our num vertices variable. The prev array contains the MST, so we'll store integers representing the vertex numbers. The cost array contains the cost to visit each node in the MST, and we store these as doubles. We're then going to initialize these two arrays by looping n times, where n is given by our num vertices variable. Following the pseudocode for Prim's algorithm, we're going to set each cost value to be infinity, and this is given by the limits header in the STL. We're also going to set each prev value to be -1 to indicate that it hasn't been filled in yet. This is because our vertices are labeled 0 to n, so if we just leave these initialized to 0, it's going to create some confusion when building our MST. The last step of our initialization is to set the cost of the start vertex, given by the parameter u, to be 0 to indicate that this is our starting vertex. Next, we're actually going to build our MST. We're going to start by initializing an instance h of our priority QE, passing in num vertices and the cost array as the arguments for our constructor, and again looking at the pseudocode, we then keep looping until the priority QE is empty. Inside this loop, we call the priority QE's delete_min function, and store the return value in a variable v. Next, we loop through all the edges starting from this vertex v. To do this, we first create a for loop that loops n times, where again n is given by our num vertices variable. Then we check if this vertex z that represents the current iteration is not equal to v and contains an edge connecting vertex v to z. So if the entry in the edge matrix given by vz is greater than 0, we have an edge between the two vertices. Next, we're going to check if z is in the QE and that the current cost to reach z stored in our cost array is greater than the cost given by the adjacency matrix. Recall that at the beginning, all our costs are initialized to infinity, so we should expect this conditional to pass at least once for all the vertices. If this conditional passes, that means a better solution is now found, and we'll store this by assigning cost z to edge matrix vz. We're then going to store this vertex into our prev array, and we'll call our priorities QE's decrease key function. Pass in the vertex we want to change z, and the new value to store in our priority QE, cost z. Once the priority QE is empty and this loop completes, we should have our MST stored in the prev array and the costs in the cost array. What we want to do now is return the total cost of the MST. Recall that the purpose of an MST is to find the graph that connects all vertices with the smallest cost. All we need to do is sum up the costs we've stored and return this value. So we'll start by creating a sum variable stored as a double, and then we'll loop n times again, where n is given by num vertices. Then we'll increment sum by cost I. At the end of this function, we'll clean up the dynamically allocated arrays we created at the start, and then we'll return this value sum. That completes our implementation of Prim's algorithm using a priority QE. Before signing off, let's test the code to make sure everything is working as expected. For this purpose, I have 4 test input files defined with their expected outputs. We'll pass in these input files into our code and check that the console output matches the expected output. I encourage you to write your own tests and verify that everything is in fact working as expected. First, we compile our code, and then we pass in test01.in as our input. Once we pass this in, we get this output, so we can compare it to the test01.out file and see if it's right. Our output matches, so that is a positive sign. Next, there's test02.in. We do the same thing that we did for test01, and we again compare the output. It looks like this test also generates the correct output. Test 3 also matches the output, as does test 4. It looks like everything is working well in our implementation of Prim's algorithm. That completes the video, guys. I hope you enjoyed learning about Prim's algorithm and minimum spanning trees. If you have any questions, feel free to leave a comment below. Also, please share this video, give it a like, and subscribe.